Hello, it's James from XRobots.co.uk. This is part 1 of my version 2 life-size BB-8 project that I've got just here. So I've done quite a bit of work on this already. This video is actually being made in early October 2015 and I don't know when it's going to be published. So I'm going to be doing work on this before I publish it so that I can make it work. And as you can see, I've already done quite a bit of work on this. So I already made one BB-8, which is a 5-part series in my channel. That was designed as a robot that balances on a ball, so all the electronics were in the head, including omnidirectional wheels, an inertial measurement unit and an Arduino processor with motor drivers and batteries. The head actually balanced on the ball and the ball was effectively empty. Now I built that version based on only the 3 seconds of footage of BB-8 in the first Star Wars trailer. The first video in that series was published the day after we saw the real BB-8 at Star Wars Celebration at Anaheim. So obviously I had no idea what BB-8 looked like really or what it did, apart from that 3 seconds in the trailer when I started the design. Since then, quite a few other people have started to build BB-8s, and a lot of people have taken the approach of having a ball, of course, with something that drives around inside and the head stuck on with a magnet. Now there's several issues with having an omnidirectional thing, a bit like my head on my first version, but inside the ball, mainly finding a ball that's perfectly smooth on the inside and the outside, so that the thing can drive around all the way around inside without any lumps where the seam is. If you sort of fix two halves or two hemispheres together without a seam and you fix them permanently, then obviously you've got the issue of servicing and charging batteries and all of those things, which creates another problem to solve. So I've taken quite a different approach with this version. It is something that drives in the ball, but it does it in a completely different way. So let's take a closer look. So firstly, the head I've got here isn't actually going to be the head, it's a polystyrene dome with a paint cap stuck on, so we'll chuck that to one side for now, as just to show the appearance of BB-8. In this one we've actually got a sort of barrel-shaped ball here, which is one section of the ball. Of course, if it had the sides on it, it would make a complete ball. It's 1/2 metre in diameter, which I think is roughly the right size for a full-size BB-8. And it's in fact entirely 3D printed, so each of these sections, there are 16 of them. These are all printed on a Lulzbot TAS, and they took about 2.5 hours each. The black rim ties them all together. There were screws in here. They're all printed in ABS, so it's all solvent welded together with acetone. So now I've been able to take the screws out, and this is incredibly tough. So inside there, what I've got is essentially a central hub, and that is driven around by a motor. You can just about see the orange wheel that drives it. This is actually a windscreen wiper motor inside there, which is driving the internals around, and there are little wheels spaced around in there. You can maybe just see one of those orange wheels right up in there that holds the internal hub away from the outer barrel shape, and that is essentially how it drives forward. So this entire central piece turns around, driven by that wheel on the outside rim. So to turn on the spot, which is a key feature of BB-8, I've got this ring here of 2p pieces. Each of these holes here has 10 2p pieces in. Again, this is a 3D printed ring, and this spins around, and it's driven by these 2 motors, each with their own motor driver, which are on each side. And that spins around. As it does so, it forces the ball to turn in the opposite direction. So let's give that a drive on a smooth floor. Obviously it doesn't work particularly well on carpet because there's quite a lot of friction, and then we can see what other issues occur with this sort of design. Alright, so it's powered up. I'm powering all the motors on 24 volts, so I've got 2 L298s, one for each of the flywheel motors, and a big motor controller called an MD03, which is a 20 amp 24 volt driver, and that is driving the motor inside. So if I give it a spin, that part works quite well. Driving forward and backwards, however, is a different story. So balls, of course, even with a heavy weight in, are still inherently unstable, and therefore really weird things happen. So I've got a variable speed control over this. The main issue is, of course, to shift its weight forward to actually cause the ball to roll means shifting the inside to an angle, and then of course that makes it really unstable. It also means that the ball sort of catches up and the motor is swinging around inside when it's driving. So we need to add some stability to that. Driving and trying to steer. Let's see if I can do it. is actually not terrible, but there's quite a bit of recoil. And then we get into this situation where it starts to wobble sideways, which, if I'm not careful, it's actually really hard to drive, causes it to tip over all over the place. So we need to do some things, there we go, to fix that. Obviously there's no sides on the ball, which would help a bit, but it may make it even more wobbly. So one really good question is, why would I want to build it like this? Why would I want to build it that essentially it drives in one direction and turns on the spot? And of course it can still be made to have the appearance of BB-8 by having the head on top that rotates all the way around. So, you know, the ball can rotate and the robot head can rotate, and it can, eventually the head will be fixed on this axis on a magnetic coupling as you'd expect, and that will move in all directions within this channel. So the head can sort of go down on one side and turn and move all the way around. So that's not really an issue. But essentially, with no sides on the ball like this, if I can stabilise it, that gives me one specific advantage, which is that the sides of these can be anything really. They can be hollow or they can be a 3D printed frame. I can put panels that open in here, so BB-8 looks like it's got utility arms and flaps and panels and things which open, so I can have all of those features on there because it never drives on the side of the ball. The LEDs we saw on the stage version of BB-8, I can put all of those in there, and I've got no issue with there being, you know, anything rubbing on that on the inside. Also means I can have access panels to get to the batteries for charging, for maintenance and everything else. So the main issue I've got, of course, is with stability. So thinking back though, I've already built a robot that balances on a ball, so it's not going to be too tricky to stabilise this, at least in one axis. So the next plan for this project is to try and stabilise this with an inertial measurement unit. I'm going to be using an inertial measurement unit from Adafruit. Now, when I did my ball balancing version of BB-8, I had to do all of the maths myself to combine the sensor data and do the complementary filter to do a high pass and low pass on the accelerometer and the gyro, and then do some other hardcore maths really, when the processor wasn't really fast enough, which is why it isn't very stable. The chips I'm going to use now are the Adafruit chips with sensor fusion, which means that lots of that maths is actually done on the board for you, and it just gives you the numbers, so that's going to take quite a lot of processing overhead out of the problem. So I probably will get away with the 8-bit Arduino that's already installed in there. I may have one or two Arduinos for parallel processing. So stabilising this front to back should be easy enough by just basically shifting the inside to catch it and keeping it stable. Obviously I could really do with some more mass in here, but if I put more mass attached to the ball without it being on the rotating flywheel, and the flywheel has to push more in the opposite direction, if I put more weight on the flywheel to make it stable, then I need more power to turn it, so I need bigger motors and more batteries, which will oppose it being turned. So I'm going to leave it as it is and try and be clever and fix this with an inertial measurement unit and some processing. The other challenge, of course, is stabilising this way. It currently has no way to shift mass this way, a bit like the Sphero toy, other than quickly turning and trying to do it that way, which of course won't really work with this design. I do have a plan for stabilising left to right, but we're going to talk about that in future episodes. To control this, I'm currently using a standard 2.4 GHz RC 6-channel controller. I'm only using one stick there for driving and spinning the pendulum, and there's a radio control receiver just here, and basically the motor controller, the MDO3, which is just in there, can be controlled by an RC signal straight from that receiver. It does other things like I2C and some other clever stuff, but for now that's all it's doing is just being a radio control motor controller. The rotation here is controlled by an Arduino, and I'm using the pulse-in function of Arduino code to read the PWM from this RC receiver. So what I'll eventually be doing, of course, is trying to receive a signal, processing it with inertial measurement units, and getting that to drive the wheels around. So the problem with that is that pulse-in isn't very stable. Ideally, I need to use interrupts to read this signal properly, and there is quite a lot of good code out there for people who are using Arduino in radio control projects. However, it is fairly heavy. Pulse-in is one line that will read the channel, and it's fine if you've got a big dead spot. But that's really going to confuse my algorithms. So actually what I'm going to do is build my own controller. So these sorts of RC sets are okay, but essentially it's a bit crazy because we're taking an analog stick, putting it into a digital transmitter, then taking it through to digital, making essentially an analog PWM, and then reading that and then turning it back into analog again. So it's all a bit crazy. So we'd be much better off if we just made a digital controller that read a knob, turned it digital, then everything was digital all the way. So I'm actually going to build my own Bluetooth handset and receiver. The reason I've gone for Bluetooth and not XB or Zigbee or one of the other wireless modules is that Bluetooth works on a lot of devices like phones and tablets. So for now I'm going to be using a pair of these Maplin Bluetooth shields, which are from Maplin Electronics in the UK. One is configured as master and one is configured as slave. I'll have a quick look at the setup in a moment, but essentially it means that I can actually pair to the robot from my smartphone, and eventually I can write an app to control it. For now it's going to be a hardware controller, but that's why I've gone for Bluetooth and not one of the other wireless communication protocols. So this is the item here. It's $19.99 in the UK, which is about right for a Bluetooth shield. You can buy just the Bluetooth modules, which is that green board, on eBay for not very much money, although I haven't had much luck configuring those on their own. So you can pretty much ignore the 3-star review or 2-star review, depending on where you look on the page. There's a few people saying they're terrible and some people saying they're good, but not many reviews. The best thing to do here is go to the overview and go to the support page, and that takes you to the Linksprite wiki, which is appears to be the Chinese manufacturer of these, and in fact it is fully documented. So this is the board. It's a shield that fits onto an Arduino Uno. So lots of specifications. The important thing is the little switch and the jumpers. So make sure they're set like this. And essentially all you have to do to pair a pair of them together is put this code into one, which is for the slave, and further down the page there's some code for the master, and you program the Arduino that it's piggybacked on, one with slave and one with master. Then all you need to do is open a serial terminal. They're showing it with XCTU here, but you don't have to use that. You can use the Arduino serial terminal. Essentially all you have to do is open it up at 38400 board, and it should test Bluetooth, provided you've put the switch in the right position, and it'll all work. All you need to do then is send a capital S to the serial terminal, and it should say it's OK, and then put the switch back in the other position, and it should work fine for both of them. In fact, on the master I did get an error that said failed, and then it said everything was fine, and in fact they do work. There's also an example here for pairing to a phone, which I found has worked fine. The only thing I couldn't get it to work was connecting to a PC with a Bluetooth dongle in, but I'm not sure if that's a Windows issue or an issue with the dongle, but it certainly works on my Android phone. So basically I've put the code on both of them, and once they're set up you should see them pairing and 2 red lights coming on. So let's have a look at that. So here they are. I've got the slave and the master labelled. It doesn't really matter which way round they are for this. Essentially what we're doing is making a transparent serial link, although I will put the slave in the robot, so eventually I can pair to it from my phone, and my phone will become the master. For now the master will go in the hardware controller. So I'm going to power these up. Let's power up the master. I'm just using a USB stick here, no PC attached. So you should be able to see the green lights flashing and the power lights on the Uno. And we'll just power up the slave as well, and you should see those lights flashing, and then eventually they should say hello to each other. Yep, now both the red lights are on, which means they've paired successfully. And essentially what we've got here is a transparent serial link on these pins, which are jumpered. So it's set to 6 and 7, which you can use with the Arduino software serial library. You can jumper them to 0 and 1 to use the hardware UART serial if you want, although it will cause you some problems programming the Arduino through USB, because that's where that serial adapter is attached. So I'm going to leave them on 6 and 7 and use software serial. We can now wipe away the code we used to set them up on both the Arduinos, put our own code on each Arduino that talks to software serial on 6 and 7 on both. Essentially whatever we shove in or out of those pins will go over Bluetooth to the other one. So it is a truly transparent serial link. I think Bluetooth runs up to about 3 meg, but I'm going to leave them at 38400 board. There's some mention in the instructions that that's a reliable speed. So I'm not sure why we couldn't run faster, but I happen to know that that works fine. Here's my rather simplistic remote. So this is just two 3D printed plates with some spaces in between. I've got a space to put the Arduino there with those mounting holes on the bottom layer, and I'll be able to see the shield and everything and access the wiring there through the hole. There's some other holes and things in the top surface for buttons and switches, and I've also got two big holes there which are for two joysticks. So we're going to put a LiPo battery in to power this instead of lots of AA's or whatever, so that will fit in the gap that's currently nearest to us there. So let's get those parts printed out and get it all assembled. Here's my remote assembled, so I've got those two layers there that I showed you in the CAD with the Arduino sandwiched in between. So I've got that's the power button that's going to turn it on, and that's going to be a voltage readout for the LiPo which will power the remote. I've obviously got two joysticks there, one for driving and one for head motion, which will be backwards, forwards, left and right, and another lovely pointer knob there that's quite retro for head rotation. I've also got a space there for two buttons which will be for lights and sounds and other functions. The Arduino is actually showing through this hole here, and that's so I can see the status of it, so I can see the power lights and the Bluetooth lights and the serial data going backwards and forwards. But also I can plug more modules in, so I can put another shield in there, or I can access all these pins, so I could have another module in the future that fits over this hole. It's easy to connect, or other drop-in modules, so I could have an LCD readout, perhaps taking telemetry data back from the Droid to tell me about the inertial measurement units or the voltage of the batteries. Or I could just put more controls on if I need more buttons, so that's ready for future expansion. I feel a bit like I'm driving a submarine, but that's probably because it's in BB-8 orange. So now we just need to get that all wired up and work on a bit of code to send all the data from these controls over the Bluetooth serial stream. I now have my remote built up, so it's turned on, it's got a LiPo in the front, I've got 12.5 volts on my LiPo there, which is pretty healthy. All the things are installed, the buttons work and the knob works as well. So you can see this is actually paired. I've paired this off to the other Bluetooth module. And if you watch my Ultron series in part 1, I actually did a very similar thing to this, which was just to read the data. So I've actually bridged out the Arduino to reset it, swapped around the jumpers, so that I'm just using this Arduino at the moment as a USB to serial interface. And I've got the Bluetooth link, of course, set up as a transparent link. So the data that's getting chucked in this end is going straight over Bluetooth and straight out of USB to serial. And that is currently being displayed in a terminal on the screen here. So you can see the numbers going past. And essentially what I'm doing is just reading the analogues and so on from all of these and this knob, and chucking it down a serial bus with commas in between, and then reading that data stream. And eventually I will use the read ASCII string function to put those into variables to control the Droid. So if I take this and let's just turn the knob for the head, you can see the last digit in there on the very end, going from 0 all the way up. The buttons are 1s and 0s on the front of that, and obviously these knobs here, if I wiggle them round, affect all the other values, and that's doing that 20 times a second, which is probably fast enough for controlling it. And this is 10 bits, so I've got values, you can see the top here goes to 1023, so it's a 10-bit resolution. I probably don't need 10-bit, 8-bit would be fine really for driving the motors and driving the head rotating speed. So that may get mapped down to 8-bit to a maximum value of 256, but for now it works pretty well. And it's pretty stable, a lot more than using pulsing to read an RC transmitter and receiver. So there we go, that's looking pretty good. That's all for this episode, but in part 2 I'll be actually driving the Droid using this controller, so I'll be putting the Bluetooth shield onto this Arduino and using that data to drive the motors. I'm going to be using the Adafruit absolute orientation sensor to try and keep the inside stable, at least in one axis, and it's going to do that by driving the actual angle of the internal hub for a PID controller. So in fact it will try and keep the angle constant as it's driving, and the greater the angle, the faster it will go. So instead of actually driving the motor speed with this control, it's going to set the angle, and that's how it's going to stay stable, at least in one axis. The future plans involve having 2 inertial measurement units. One of those is going to be on the head stick, which of course moves independently of the body, and that will mean that I can work out the centre of gravity of the actual whole droid by using both inertial measurement units, at least in this axis. So when the head moves forward, the inside moves back very slightly to compensate, so the whole thing stays stable. My plan for side-to-side compensation is actually to use the head reactively. As this starts to move one way, move the head really fast the other way, or in fact in the same direction, so that it stabilises it. And that's going to take some doing. So that's the plan for the entire stabilisation of this droid. So check back in part 2, there's probably going to be 3 to 4 episodes in this whole build, including finishing it off and putting the sides on. That's all for now.